Hello everyone, this is our first video on natural language processing or NLP. We're gonna start with an introduction to how you can process speech or text or stuff like that, and we're gonna focus on an example for spam detection. So if you get a text in your email or a message or something, could you classify that as a spam or not a spam? So the first thing we need to know is in natural language processing, we are dealing with words. We are not dealing with numbers. And words are categorical data, and the neural networks that we have seen, we need to multiply the weights by some numerical values and add some biases. So the input to a neural network has to be numerical numbers and not categorical. So we have to convert them to numbers. How? One way that I have explained in one of my previous videos is called one-hot encoding. And one-hot encoding is, of course, basically considering a line vector. The length of it is equal to all different, in this case, words that you have, right? And then making a dictionary, basically, and then depending on this word is in which part of the dictionary. If it's the first word in the dictionary, you give it like 1 or 0, like, and then I mean the first element of that vector, you give it the 1 and so on. So let me explain that through here. So let's say this is a text that I have, and I want to process this text. So here I said, seems like advertising for my channel, huh? EEA, Engineering Educator Academy, has free educational videos. It has covered numerous courses. It explains topics in details with simple explanations. EEA offers download demo files. Please subscribe to EEA and please share it with your friends. So clearly the text I'm going to process here is composed of a bunch of words. So how do I basically do the one-hot encoding? Well, I look for all different words, for unique words. So if I count EEA one time here, that's it. I'm not going to count it again. This has one time, I'm not going to do it. This free, this educational, and I form a dictionary. Okay, so this dictionary, in this case, as you can see, it has 25 unique words. And then to each one of them, I'm going to assign a what? Basically assign a location. So I say EA is word number 1, has is word number 2, with is word number 3. You can even sort them based on alphabetic order based on the first letter if you want. So it is closer to a real dictionary, or you can just keep them unorganized and unsorted like this. So now one-hot encoding is what? So I say this word EEA is the first word in the dictionary, and I have 25 words. So here I'm going to what? I'm going to create a vector with 25 elements or entries, and they're all 0 except for, because this is the first word, the first one is going to be 1, the rest of them are all going to be what? 0. Or if I want the word, let's say for instance demo, I say demo is what? Demo is word 19. So I go ahead and again create a vector with 25 entries, and all of them are 0 except for what? This element 19, which is 1. 20 is 0, 21, 22, 23, 24, and 25. So this is that 19th entry. Okay, that is 1, everything else is 0. And clearly you see this method of encoding is very inefficient because you're dealing with tons of zeros, and these vectors are very sparse, right? This is not an efficient way to encode the words into numbers. This is really inefficient. And one reason is, as I said, a ton of zeros that we really don't process them for anything. And when they multiplied by any gain, those zeros will just be zeros. So that's one reason. The other reason is when we are dealing with language and speech, Many languages, they have tons and tons of words. They have thousands to millions of words, just like English language has more than 1 million words. Now, many of them are not frequent. Many of them you barely hear in daily conversations. Probably a few thousands to maybe 10,000 of them are the ones that are used in daily basis, but the other words are still there, and once in a while you might see them in a text or speech or something. So if I really want to create a dictionary that I can use for basically all sorts of speech recognitions or spam detection or whatever, this dictionary has to have a huge size. It has to have 1 million entries, right? So you're going to have vectors with 1 million zeros except for one of them that is 1, okay? And when your input has 1 million numbers, imagine what size your weight matrices should be. And those processes, those many numbers, are not something that are really acceptable and welcomed in a neural network. So you don't want to deal with such sizes, okay? And another reason that is very interesting and we have to keep in mind is, if I give you two vectors, one of them is 0, 1, 0, 0, 0, another one is 1, 0, 0, 0, 0, and another one is 0, 0, 0, 1, 0. And if I call this A, and I call this B, and I call this C, and then I say, what's the distance between A and B? What would you say, the Euclidean distance? Okay, norm 2. Right? So if I want to do it a little bit more scientific, basically I can do it like this. Norm 2 of A minus B, right? What is that? Well, you clearly see it's a 1 minus 0 squared plus another 1 minus 0 squared. The rest of them are 0, so you get the 2 under a square root. If I say, what's the distance between A and C? You say that's the same thing. And if I say, what's the distance between B and C? You still say the same thing. So here, regardless of what word these A, B, and C represent, the distance between all of them is square root 2. Whether they're similar words or completely different words, their distances are the same, and this is not really a good way to put these numbers in the space. So when later you want to classify them, let's say you want to know what's the sentiment of a sentence or something, right? Or what kind of story is this if I basically describe a book or a video or a movie, whatever, with a few sentences, and you want to give me a category, say, hey, this is, for instance, action movie or drama or something else, right? How could you do that? Because they're all the same distance. So this is absolutely ineffective, and you cannot use one-hot encoding really. So what do we do? Well, the first thing is we need to know that before we pass any of these texts that we have to a neural network, we have to do some pre-processing. And one of the pre-processing steps is to take care of this problem, converting these words into numbers. How do we do that? Well, this step is called tokenization, okay? We convert these words into, we convert the sentences into a bunch of individual words or tokens, okay? And one thing you need to know is in TensorFlow, when I look at this first sentence here, which says EEA has free educational videos, TensorFlow does not look at this as a combination of 5 different words. TensorFlow consider this as one single string rather than what? 5 separate words. So before I even convert this into a bunch of numbers, I need to make sure that I break this sentence into its individual words or components, which we call a token in general, or words. So the first thing is break this down into what? Into a separate EEA and a separate what? Has a separate free, a separate educational, and a separate what? Videos. That's the first thing you need to do is to break the single string down into each one of the sentences into its tokens, okay? The next thing you need to do is, of course, convert now each one of these words into some kind of numerical value. Now, as I said, the one-hot encoding is not efficient, and you might say, why do I need all these ones and zeros? Well, if in the dictionary word EEA is the first word, then instead of all of this big thing, I just assign number 1 to EEA. And if demo is the 19th word, then I represent demo with number what? 19. So this way you just represent each word with a positive integer. Okay, this is a lot more useful, a single number instead of a vector that has a million zeros and maybe a 1 1 or something. Okay, so this is a lot more efficient. And this is what your tokenizer method in the TensorFlow does for you. Okay, now one thing is tokenizer will create a dictionary for you. Okay, so tokenizer will create the dictionary for you from, as I said, all unique words in your training data, and based on the place of each one of these words in the dictionary, it assigns them a number. Now, one thing we need to mention is tokenizer method in TensorFlow has a parameter called number of words, which determines the maximum number of words to keep in the dictionary. Okay? So, for instance, I can say, hey, make a dictionary from this text for me when the number of words equals 50. What do you think would happen? Well, here I only have 25 unique words. So if I pass 50 for the number of words, do you think it will add 25 extra words from somewhere else to this? No. So if I give it more, a value bigger than the number of unique words in my training data, then what? Then that dictionary will only stick to the number of unique words. On the other hand, if I give it a number less than the number of unique words, what happens? So here, if I change that 50 and say, let's say 20. So create a dictionary from this text for me, but with 20 words, not 25. What do you think would happen? Then it will only keep 20 words out of this 25. Now, which one does it keep? It does work based on the frequency. The words that it sees more, repeated more in this text, it will give them higher priority for being kept. So you see here, EEA, you see it all over the place. So this word is going to be kept. Okay? But maybe if you see a word like, for instance, details, you see that one place, so maybe that's one of the words that might go. Okay? So you can give it a number, and you might say, why would you give it a smaller number? Well, the reason is sometimes these dictionaries are huge. As I said, these dictionaries can be huge if your text is very large and you're dealing with a generalized, let's say, a very big train network that can detect spam, let's say, for instance, on any kind of text you give it, not just a few words that I'm using, a few sentences, then this dictionary is going to be huge. So maybe to basically manage the memory, I want to only keep the high frequency words. That's where I pick this number. And I'm not going to pick a million probably. I'm going to use a lot smaller. Maybe only the 30 or 5 or 3,000 words that people use in a daily basis. So I just use those words, okay? If you don't want to pick a number for it, you can just pass the option none. So you can say number of words none. Then it will just look at all the unique words. And in this case, it says, hey, what? I'm going to go with 25. Okay, so if you don't want to pick it, just give it a none, or you might give it a number bigger than what you think the number of unique words is, so it is going to trim it down to that number. Okay, but if your dictionary is huge, maybe you want to trim it down and give it a smaller number. So this is the tokenizer method in TensorFlow. The next thing is when you tokenize it, then what happens? So let me show you. So let's look at the first sentence here. The first sentence is EEA has free educational videos. So now I go and look at EEA. Well, EEA is number 1. Okay, so it takes 1. Then what? Then we have what? Has. Has is 2. Then we have free. Free is what? Let's go ahead and find free. That's 5. Then we have educational, which is 6. And then we have videos, which is 7. So that string should be converted into 1, 2, 5, 6, and 7. And you see it does. Okay, so it converted that sentence for you into a vector of positive integers, and then it does the same thing for second sentence, third sentence, all the way down. Now, one thing you see right off the bat is, well, the size, the number of words in these sentences are different. The first one has 5 words, the second one has 5 words, but the next one has 8 words. Okay? So the result of a tokenizer is going to be a bunch of vectors which all have what? Different sizes. Now, can I pass such a thing to a neural network? No. By the way, speaking of neural networks, what kind of neural network should we use for natural language processing? Well, since the words and speeches are sequence, they are sequence of words, so the type of network that we should use are what? RNNs, okay? They should be recurrent neural networks. Now, does it mean that's the only type of neural network that I can use for natural language processing? No. For instance, can I use convolutional neural network? Yes, actually, you can use convolutional neural networks for natural language processing, although they are mostly used for images. But if you consider these words as numbers and the pixel values in images as numbers, then basically an image and a sequence of numbers or a sequence of words, they are all just numbers. They all are treated the same way with a neural network, okay? So as long as we are converting everything to a bunch of numbers, then we might be able to use other networks too. But again, since we in convolution neural networks, there is no memory. We don't look at the previous data. They might not be really appropriate because when we talk, the next word that we provide in a sentence or a speech or something mostly depends on what we said earlier. So memory and previous values are highly big determining factors for the future words, and so RNNs are the best ones. Now, as I said, RNNs do not like you pass them something like this. They do not like this sequence of data to be what? To be passed to them. They want all of these sequences to be the same size, like that. Remember that in previous video when we talked about LSTM, we saw that the shape of this input vector, it was basically a 3-dimensional matrix, and I mentioned that for you here. It was n by t by d, where d was the dimension of the signals, t was the length of the each row, basically the number of columns, and n was the number of rows or the number of sequences. Okay, so we need a proper cubic shape for RNN, not something like that. So what can we do to make them all the same size? The answer is padding. We add a bunch of zeros to the shorter ones to make them as long as the longest one. Okay? So we use padding. Now, padding in TensorFlow could be done with pre-method or post method or post option. The default is pre. Okay? So as you can see here, the zeros are added to the beginning of these vectors to make them all the same size as this third one. Now, if you want, when you do the padding, you can say post. If that's the case, then this first row will be what? Will be 1, 2, 5, 6, 7, and then 3 zeros. Okay, so you can have them added at the end of the vector instead of in the beginning. And you might say, well, does that make any difference? Yes, it does. For different applications, sometimes you really want to have the zeros pre, or sometimes you want to have them at the end, okay? Because, for instance, remember that an RNN looks at previous values, right? So if I look at the sequence and I want to determine what word comes next, right? So let's say I want to fill the next word for you, like what Google does. It suggests you the next word or so on. If I want to look at these previous words, and I might look at all of them, but remember, the ones that are recent, they have a higher weight compared to the older ones. So these 1, 2, 5, 6, they get a small weight, but these zeros will get a big weight. And guess what? They are zeros. They don't tell me anything. They are not related to any word in the dictionary. So here I have no suggestion. Okay, so if you want to guess the next word, you better put all these zeros what? In the beginning. So when it goes toward the end, it has all of these meaningful words to look for. Okay, yeah, you see, so that's the importance. And in some other applications, you might have what? You might have the zeros at the end. Okay, so it depends on the application where to do the padding. But here, as I said, it is, you have both of these options. So these are the two important pre-processing steps that you need to do what? You need to do in TensorFlow to get appropriate size vectors and sequences, so you can pass them to what? You can pass them to an RNN. One more option I need to emphasize before we go to the RNN, and that is, remember I told you that the padding has an option of pre and post for padding. It has a few more options, so let me talk about them. The next one is this option called max length, max len. What is this? So here, you can give it a maximum length of the sequence yourself instead of it goes and finds it. So here, if you don't give it this number, right, then it goes and say, hey, the maximum sequence length I have is 8, so I'm going to use 8, okay? And I'm going to pad the rest of them that are not 8 with a bunch of zeros. Now, sometimes you can give it what? You can give it this number yourself, because you want to determine the n, the parameter n, the size of the sequences, the length of the sequences, okay? In that case, you might say, well, what happens in this case if I give it a 10? So if in this case, instead of 8, I gave it a 10, what would happen? Well, guess what? Now all of them should be length 10, so even this one that was the longest, it's going to get 2 extra zeros as well as everybody else. Okay? Yes? So if you don't want to get a bunch of extra zeros, you might not provide a number, okay, and let it find it itself, because if you do, you're going to get a bunch of zeros. Now you might say, what if instead of 10, I gave it 6? If I gave it a number smaller than the maximum real size sequence, what would happen? Then you'll get truncation. Then now I have to get rid of 2 numbers from this largest one. And the question is, which one do I take off? Do I get rid of 15 or 16 and 16, or do I get rid of 1 and 11? That is an option that you have. So for truncation, if you want shorter sequences, you might give it a pre option or give it a what? A post option. This is the pre option. This is what? The post option. So you have all of these options. Okay. If you want to change the size of what? The size of this, the number of columns of this basically training data. Okay. So now you might say, well, I'm ready now. I got my data. Let's go ahead and pass to RNN. And I say, well, wait a second, not so fast. there is one extra thing you need to do. You might say, what is that? And I say, this is called an embedding layer. Before pass it to RNN, LSTM, whatever it is, an element layer, you need to what? You need to do something called embedding. What is embedding? So let's talk about it. Remember, as we talked, the input to an RNN must be what? N by T by D, where N was the number of rows, T was the number of columns, and D was the dimension. Here, instead of N by T by D, it's going to be V by T by D. D is still, and let's talk about these three parameters. These are three important parameters in NLP. So what is V? V is the same as N, the number of sequences. Well, in this case, V is the number of unique words in this dictionary. Okay, so V here is what? For this example, that's 25. The number of what? Unique words, that is your V. What is T? T is the maximum length that you have. This 8 here is what? Your T. That is the maximum size that you have, unless, again, you change it with this max len. So basically, this max len in general is your T, the largest size of sequence you have, and the number of rows is what? V in general. And then D is the dimension for each one of these sequences that you're going to pass to the RNN. And you might say, well, isn't D 1 in this case? Well, not necessarily. Why not? Because remember, the type of thing I'm passing to my neural network is a bunch of scalars like this. 1, 3, 25, something like that, huh? Yes? So if I just go with that, then each word here is going to be what? It's going to be a vector of size 8 with 8 elements. So they're going to be in an 8D space, right? All of these words are going to be some vector, some arrow, some number in some 8D space. And these numbers are along the axis could be some positive integer, right? So they are not going to be in all of this 8D space. They're going to be only in a portion of it. For instance, if instead of 8 it was a 2, then, right, this is your 2D space. And since all of these are positive integers, guess what happens? All of these numbers will only occupy the first quadrant. The rest of this 2D space will be unused. Okay, so you're squeezing all of those numbers in one quadrant, and that's not really a good, efficient way to map them all into this 2D space. Okay? Plus, another thing, these numbers can be extremely large. Remember that if you have 1,000,000 words, one of these integers could be, or some of these could be million, 900,000, 800,000. So you get some data here toward the origin if they have only some words that have letters A and B, and some of them might be all the way down here toward 1,000,000. Okay, yes? And these words are going to be far away from each other, although meaning-wise, this word and this word could be close. So one thing we need to do is to squeeze this space a little bit further down, bring the scale down instead of 0 to 1,000,000, bring it to some smaller scale, 1, 2, use all of these subspaces or quadrants of this multi-dimensional space. And another thing is, as I said, if you have what? If your sentences are very long, if I have a very long sentence, that means that sentence is dominating the size of the space in which I map everything. So I might have a what? I might have a ton of short sentences, but one of the sentences is huge. Like I have a bunch of sentences with 4 or 5 words, and I have a sentence with 30 words. Should I use a 30-dimensional space just because of one vector that is very long? That's not really a good idea. So here, with this embedding layer, we try to pick the dimension of the space to which we project all of these vectors with positive integers. We project them all into this new space, and this D, the dimension of that space, we choose as a hyperparameter. Okay, this D, we choose it as a what? As a hyperparameter. Good? So, for instance, if I pass this vector 4 and 20, which is a sentence with 2 words, like hello world, if I pass this to the embedding layer, then the embedding layer would convert that into what? Convert that 4 into this, and convert that 20 into what? Into that. Okay? Yes? So here, D is 2. I'm talking about a 2-dimensional space. And I do it like that. Or I can make D bigger and so on. So, question is, what kind of D should I pick? Small d, big D, what number? There is no magic formula for that. The only guideline is if the sentences in general are long sentences. T. And if you have a ton of words in your dictionary, then you might choose what? A larger value for D. So here, instead of N, I need to change it to B. So if V, the number of unique words, is too much, you have a big dictionary with long sentences, you might also use what? A bigger, basically mapped space, so you can get the data enough of basically distances. Not very large, but sufficient distance. So that is what your embedding layer does in TensorFlow. And I know you would ask this question, that where do these numbers come from? 0.25 and 0.1, 0.6 and negative 0.2. How are they related to 4 and 20? How does this embedding layer work, right? How does the mapping work? So let me explain that a little bit for you. So these are going to be the inputs to LSTM. And when I go into LSTM, I multiply these input x's by some w's, right? Let's say wxh, correct? Transpose times x of t, and plus something else. I pass it to a sigma function, and that is going to be like h of t, huh? So you see that I need to multiply these x's by some weight matrix, correct? So now, let's say when this x is number 4. 4, if you remember, in one-hot encoding, it is corresponding to what? It is corresponding to the first number being 0, second number 0, third number 0, fourth one is 1, and the rest of them are all what? 0 all the way to the end, correct? Now, if I multiply a W matrix by this X, what's going to happen? So here I have this huge W matrix, X of H, transpose, multiplied by this. What do you think I will get? You are right. All I would get is basically the 4th row. So the result of this is going to be the 4th row of WXH. So whatever W matrix that I have, whatever WXH matrix I have at the moment, I go ahead and pick the 4th row of it, and that is going to be this result that you can see here. Or I go and pick the 20th row of that W matrix, and that is going to be this guy. Okay, so this is your embedding layer. Now, one more thing about embedding layer, one last thing about embedding layer is sometimes we don't form our own dictionary, and then from there we get all of these numbers and the results of the embedding layer. Sometimes we use the results of pre-trained networks that were trained on a ton of words, like word to vec or glove. Remember, we had pre-trained networks for convolution, right? We had these, for instance, the mobile net and so on. So these GLOV and Word2Vec are specifically trained for natural language processing. So you can use those if you want. You can use the embedding layers of this pre-trained network instead of you create your own dictionary and embedding layer and everything. You can use those, but these embedding layers and those weight matrices they have, okay, you are not going to change them. You're going to freeze these embedding layers of these. Just add the last part, the dense layers of them, to perform some required tasks. Remember transfer learning we talked about? This is a similar thing, okay? This is transfer learning, but for natural language processing instead of image recognition, right? Or classification or something. So you can use those as well. But remember, these guys are huge. So if you're doing a simple task, you might not use these unless you want, again, some NLP task or software that is working on general text or general speech. Then you might use these big ones. And hopefully in one of my future videos, I'll use one of these and show you how to go with them. Okay, so now, so far, we have an input layer, which brings the numbers in, which are pre-processed. So here, the numbers are tokenized, and they are padded, okay? And then we pass the result of that to an embedding layer. So the tokenizer or tokenization and padding, they have been done here to these inputs. Then we pass them to embedding layer. Now the result of embedding layer is an appropriate vector with appropriate size v by t by d, which I can pass to RNN. And LSTMs, because they have memories, and long short-term memories are typically very appropriate for the kind of this task that we're going to do here, like spam detection. So here we're going to use LSTM units. And remember, LSTMs, they have the number of neurons, m, which is a hyperparameter to choose. Then finally, let's say in this case, we're going to do a binary classification. We want to see whether a text is a spam or not a spam. So our final layer should be a dense layer with one single neuron, because the output should be either a 1 or a 0, a spam or not a spam. And the activation function for that is definitely what? Sigmoid, right? If you have a multi-class, then it would be the softmax, but here we use a sigmoid because the output is binary. And one thing before this between the binary and LSTM is this: the result of LSTM is a multi-dimensional vector, but when I pass this multi-dimensional vector, I cannot directly pass it to the sigmoid. Sigmoid will take one input, n, and it will return 1 over 1 plus e to the negative n, huh? So you need to pass to it a scalar, not a vector. So how can I convert this vector into a scalar that is appropriate for passing to sigmoid? I can use a global max pooling 1D. So I apply a global max pooling 1D on this vector, convert it to a scalar. Now I can pass it to the sigmoid. So between LSTM and dense, I need a global max 1D pooling layer, okay? And now my network should be what? Should be ready. Good. So now let's go ahead and look at the TensorFlow code. So here we need a bunch of things. I'm bringing a CSV file, which is basically for which I need Panda to get the read CSV method. And I need to, at the end, plot some loss function and accuracy. So I need matplotlib. I need NumPy, as always, and I need a ton of things from TensorFlow. Also, the data in this CSV file is not broken down into test and train, so I need to bring train test split from scikit-learn model selection. And then from under TensorFlow Keras preprocessing text, I need to bring tokenizer, and from under preprocessing sequence, I bring path sequences. So these two are for preprocessing. From under layers, I need to bring a dense input, global max, pooling 1D, LSTM, and embedding. And under models, I bring the model. Okay, so the first thing is get the CSV file, which is a file called spam. And I'm gonna only use the first two columns of that. So it's an option that you can pass to read CSV. If it has several columns, just I want the first and second column, say, hey, use column 0 and 1. And you can pass a specific type of encoding. So here I basically added that to my list of files. And here I show you the header of it, the head. So you see the first column are the labels. So whether the label of the text in that email or the text message is not a spam or what, a spam. And on the second column is the actual text or the actual email, right? So each column here is either a label or a data. Okay, this is the format of this CSV file. Now, these labels here are not numbers. These are not numbers. Not only we have to convert all of these text to numbers, we have to convert these labels also into numbers. So here I create a binary label for them, and binary because I only have spam or not a spam. So how do I do it? I say go to df, and df is all of the data I read from the CSV file, the two columns. Go to the label column, right? And then dot map, use the map method where if it's a not a spam, assign it a 0. If it's a spam, assign it a what? Assign it a 1. And then the values of this temp, call them y, and here I show you the first 5 values in y. You see the first two are 0 because they are not spam. The third one is a 1 because it is a spam. And then fourth and fifth are what? Not a spam. So you get what again? 0 and 0. So you see this one is perfectly converting, mapping those not a spam and spam into zeros and ones. So the labels are good now. Then the data column of this, as I said, is not split into training and test data. So here I have to do it myself. So I use train test split, df column data. And you also need to pass the labels. So it breaks everything down into train and test labels and data. And I use 30% of these columns or of these sentences for test and 70% for what? For training. So you see df train, df test, y train, y test equals that. So I got my split. Now I need to do the pre-processing. First, I create the tokenizer object and I say the number of words max that I think you might need is 10,000. Okay? And you'll see if 10,000 is enough or not. Remember what happens if this number is less than the number of unique words that you have in all of this second column under data, right? You're going to lose some of them that are low frequency. And if this guy is bigger than that, then nothing happens, okay? So here I found that 10,000 is more than those, and so I just use 10,000, or you can just not assign that. So here I say 10,000. I created the tokenizer object, and now I use the method called fit on text. And then I pass to it all of my training sentences. So what does it do here? Basically creates the dictionary for me. This part will create the dictionary. Now I apply the method called tokenizer.text to sequence. And this is the part that it looks those words into the dictionary, finds the corresponding positive integer number, and basically pass them to those words and create vectors of positive integers for each and every one of the sentences, as you can see. And it does it one time on the training sentences, one time on the testing sentences. Okay, so here, if I want to add that for you, here is creating the dictionary. Now this dictionary has how many words? You can use that by saying tokenizer.word_index. First of all, and here the length of that is the number of words. So then what is this word index itself? It's the entire dictionary. So I say tokenizer word index means show me the dictionary. Here I'm saying, hey, print me the dictionary. This is the dictionary. You can see it here. It says I is 1, 2 is 2, U is 3, A is 4, and it keeps going, right? Yes? Now, how many words are in this word index? If you see, the number of unique words is 7381. Okay, you have 7381 unique words in that CSV file. And this is one of your important parameters, V. Then remember that some sentences are longer than the others. We need to use padding. So I use the pad sequence method that I got from under Keras pre-processing sequence. I bring this, and then what? I apply it on the sequence train. And now this guy that has all the zeros, I call it data train. And shape 1, the number of columns of that, I call it T. And T is the length of the sequence. This is another important parameter. This is the maximum size of the sentence you can have. So now I use that for max length, and I apply it to the sequence test if I want to get my data test. Okay, you see last time I didn't, and it didn't need it. It found this T and it used that T. This time I can pass that T as this option max length. Remember, if I use a number bigger than this T, I get extra redundant zeros. If I use smaller than this T, then I'll get truncation, and then I can have truncation options here, okay? So here I can, like, for instance, if I use half of T, right? Then I can use what? I can use the truncation, You saw that right here when I clicked here, right? You saw that the options for this pad sequence is what? Truncate. So you can add an option like this. You can say what? And truncating post. Or and truncating what? Pre. Yes? So you can do that if you want. I don't recommend you do it because you're going to lose a lot of your information. But remember, all of these options you can add. And again, here, when we did this padding, we could do what? We could do this padding with basically pre or post, So we have all of these options for the pad sequence here, and I just try to show you those options. Here, by the way, I want to show you the first sentence in the data train after adding all the zeros. See how it looks like. If you look here, look, this is going to be the first sentence. Clearly, it shows the largest sentence in your data is much larger than the first sentence. Because if you look, only this portion of it has non-zero values. The rest of it is pre-padded with zeros. So you have some sentences that are very long, right? You clearly see that. And this first sentence is not as long. Now you might say, what is the size of the longest sentence? Well, all you need is to look at the shape of train data. This is shape 1, right? But you can also look at what? Let's see if because I did not print T. I determined T, but I did not print T. So what I could do was, I could also what? Print T here for you. Yes? And maybe I do it right here. Okay, let's see. Yeah, 189. Okay, so there is a sentence here that has 189 words. And again, the number of unique words, V, is 7381, which is less than 10,000. So all the pre-processing is done and it's all good. Now let's move on about talking about the network. The first thing we need is an input layer. The size, the input of it is T, right? T, remember, is that 189. Then we go with the embedding layer, and the size of the embedding layer is v plus 1, and d. D, remember, is the dimension that we have to choose for the output of the embedding layer. It's a hyperparameter we choose. Here I went with 20. You can change it. Okay, you can use a smaller space size or a bigger one. The only option you might say is, why is it v plus 1? Shouldn't it be just v? No, because the embedding layer, the index of it starts from 1 really, not from 0. The index 0 of it is preserved, so it starts from index 1, therefore the size of it should be v plus 1. Okay, the size of it is v plus 1, and pay attention to this part. Okay, pay attention to this part, that when you choose an embedding layer, make sure this guy is v plus 1. So here x is this embedding layer applied right after the input layer. Then right after the embedding layer, which is now called x, I apply LSTM with 15 neurons. And again, this 15 is something you have to choose. And here I use return sequence true. And then I apply the max pooling on the entire sequence, get my scalar. So this global max pooling is applied right after LSTM. Finally, I have a dense layer with 1 neuron because I'm doing binary classification, and so I also use sigmoid function. So this x is the entire output of the network. If you want, you can call it output. So now I use the model command and I pass it the input I and the output x. It creates the model for me, so the model is created. Now I choose Adam for optimizer, binary cross entropy for loss, and accuracy for metric. I use the fit to start the training data with data train and white train, 10 epochs, and for validation I use data test and y test. And you see the loss started at 0.46, went down to 0.009. The accuracy started at 86% and went to 0.999. Even on the test is 0.98. So it did an amazing job only in 10 epochs. And here is the plot of the loss function on training and testing. And here is the plot of what? Accuracy, again on the training and testing. Okay, so you see that it could actually do a very great job on spam what detection. So it could basically recognizes all of these true labels that were created by human beings. So these labels are all basically created manually. And our network is now trained. So if I pass one of these sentences on random, it should be able to generate the appropriate left column with a 98 to 99% chance. Okay, so hopefully this was useful to you and you learned some very basics about natural language processing. The tasks that you can do in natural language processing are huge. This is just a simple one like a spam detection. If you want to do other jobs, the type of network might change or will change, and you might need a bunch of extra things to get the job done, and I'll try to make some videos relating to those as well. So thank you so much for your attention. I'll see you in the next video.